All right, guys. So a couple of you asked for a little bit of extra help on this. So for now, let's just look at the blue, and then the particular problem is the what's in red. So let's just talk about the blue in general. So we're talking about logistic differential equations. We changed the model of exponential or first order differential equations because those grew exponentially and we realized we had to change the model. And so we created a model that looked like this, where it'll grow exponentially for a bit and then it'll peter out. And so this was the part that we studied earlier that you guys were all set with. We added this so that the growth rate approached the carrying capacity, this whole term would become zero. So then the curve would have to flatten out. Anyway, this equation up here is our logistic differential equation. P stands for population, R is the rate of growth, and K is what's called carrying capacity. This value, where the growth rate peters out, is right here, right? Like it is our horizontal asymptote as we go that way. It's not our horizontal asymptote as we go this way. That is zero. Anyway, the equation looks like this. That's what's important to know. So let's talk about this particular equation. We should be able to look at this equation and go, hey, if we distribute this RP, we'll get a constant times P here, and then we'll get like a minus a quadratic, a P squared times a constant. That's of the same form, right? Even though it's not written the same, it's of the same form. So just like linear equations, we can rewrite things and move pieces around to make it to figure out what the slope is. That's the big idea. So anyway, we need to move things around. Really aiming for that 1 is the key. So what do I factor out of here where I'll end up with a 1? That's the big question. So I'm going to let you kind of pause and think about that. But I need something that looks like this. So I'm going to have a number here and a number here. What do I factor out of this to get a 1? The answer is 5p. If I factor 5p out, this term becomes a 1. And then I'm going to rewrite this just a little bit. I think we all realize that 0.002 is the same as 2 over 1,000. And we've taken out a p, so we're going to have a p. Not quite done. I pulled a 5p out of this, so that means that I also needed to have pulled a 5p out of this. So I'm going to have to multiply this by 1 over 5. Right? So although I factored it out, I've kind of taken my time. And if I multiply this back in, well, the 1/5 and the 5 will cancel out. The p and the p will become p squared, and I'll be left with that. So everything is good. So now my job is just to simplify this, really. So let's do that real quick. So the 5p stays the same. 1 minus 2 over 100 is 1 over 500. 500 times 5 is 2,500. 1 over, so p over 2,500. So now, if we start answering the question about, I don't even remember what the problem was about, but they said, well, when p naught is 100, what is the carrying capacity, or what is the limit as t approaches infinity when p naught is 100? Well, if we, whoops, that's not going to work. I think you can still see that, yeah. Remember that we just calculated this equation. We know if the population is 2,500, that no matter what the number is, whatever our p naught is, it's going to be approaching 2,500. So the answer, what is a limit as t approaches infinity when p naught is 100? Well, it's this curve down here. Let's say this is 100. It is 2,500 population. What is it when it's 1,500? Well, maybe it's this curve up here, but it's still 2,500. What is it when it's 3,000? Well, if you remember from the graph before, we said all the numbers above it would be coming down into it. So it's, again, 3,000. So all these answers here, 3,000. The next question, though, was when does this thing grow the fastest? There's two ways to think about that. The first way is the, let's go the first way being hardcore calculus. Hardcore calculus would say, well, when is the growth rate the fastest? We care about when this is a maximum. Well, this is a maximum when the derivative of this is 0. So we could do something like this. I'm just going to erase this. We've seen this answer. So when does this grow the fastest? This is the calculus way to do it. We take the derivative of both sides. The derivative of p with respect to t is 1, so 5. And then this is very basic derivatives, 0.004 times p. We set this equal to 0. Now we've got a linear equation that we're solving. So we subtract 5, divide by negative 0.004, and that equals p. And we will very quickly find out that this answer is, 1250, 1,250. So when the population is 1250, it's growing the fastest. We could have done this a much easier way, though. The easier way is to look at this and go, oh, this is a quadratic. It's shaped this way, right? It's an upside down quadratic. So the maximum is here. We've already factored this, so we could have looked at it. I should have left it up. So I'm going to put it right here. We could have looked at it in factored form, and the factored form was 5p times 1 minus p over 2,500. We could have gone, oh, our two zeros are 0 and 2,500, and we know it has this shape, so the max must happen right at the middle of that, right? Because we know quadratics are symmetric. So we know our max is at 1250. We don't know what it is, but we know that that's the max. Great. Or there's a third way we could have looked at this. And I'll just do this last one, and I will leave you guys to it. The third way was to look at this graph. And this one is a little bit more of a guess, but intuitively it's right. Here's our carrying capacity of 2,500. And we know that the graph starts down here and goes up and does that. So it makes sense. Our maximum rate of growth would happen at the inflection point. So it makes sense that it would be right there. That is halfway between 0 and 2,500. So again, it's at 1,250. Anyway, I hope that helps you. If you need more help, please send me an email. Thanks. Bye.